Right, welcome back everybody. It's my pleasure to introduce Professor David Dunmur. David started his scientific career in Oxford, where he did his PhD with David Buckingham. Then after several postdoctoral periods in the UK and also in the US on a Fulbright fellowship, he moved to Sheffield, where he became Professor of Chemistry and ultimately also head of the department. He then moved on a full research position to the University of Southampton, where he retired a couple of years ago, and he's now a visiting professor of the University of Manchester and also an advisor to our network. And today he's going to tell us about liquid crystals, their structured fluid for applications.
Okay, everybody hear me? Well, thank you for that introduction, Dirk. It's a great pleasure to be here and to talk to you a bit about conventional liquid crystals, that is, liquid crystals formed from small molecules. As we've seen, we've extended the scale, or I say we, collectively, experts in Oxford and other places have extended the scale at which we can see liquid crystalline behavior from molecules up to colloidal particles. So this presentation is really quite useful, I hope, in bringing things up to date to where we are with liquid crystals, that is organized fluids, and where the colloidal systems can take over and move on to many, many new applications for the benefit of all, I'm sure. The liquid crystal story is a European story, as I hope will become clear, but the development of liquid crystal technologies has been global, as you will be aware, and of course we are relying in this lecture hugely on liquid crystals. If we didn't have liquid crystals, this presentation wouldn't have happened. So they're quite valuable to us. I should also say that Eindhoven is a rather special place in the liquid crystal story, as I will point out later on, and so it's appropriate to be here. The first slide has popped up. Never mind. It's always difficult talking to a general audience of mixed backgrounds and so on, because some will know a great deal, some will perhaps know somewhat less about the topic, and so I don't want to assume too much. So it's going to be a fairly basic presentation, but I hope there's something in it for everybody. I'm going to try do some demonstrations. The demonstrations that you saw in the previous presentation were very high tech. These are very low tech, but let's hope that they work. I should first apologize for giving this lecture in English rather than Dutch. You'll probably be aware that not many English people speak Dutch. However, I will try to avoid to confuse you too much. We do in English have a description of the language of total confusion, and it might not surprise you that we call it double Dutch. So I'm not speaking in Dutch. I shall try and avoid double Dutch. Actually, in England, as in many other countries, we use the term Dutch to describe lots of things, not always in a favourable way. For example, if you're invited to a Dutch treat, then you end up paying for it yourself. I do like the idea of a Dutch feast, though, which I only learnt about recently. And a Dutch feast is a party where the host gets drunk before the guests. So let's move on to the topic of the talk, liquid crystals. What are liquid crystals? And a slide like this, as you've already seen, the Greeks introduced us to the states of matter. They identified 3 states of matter: solid, liquid, and gas. And then, well, they thought fire was also a sort of state of matter, but we can forget about that. However, and that description served pretty well for many centuries, but it was not quite the whole story. And liquid crystals, as the name implies, is another state of matter, the 4th state of matter. And it sits between the solid state and the liquid state. And these are accessed in terms of molecular systems, at least, by changing the temperature. But as was explained in the previous talk, you can also access these different phases in colloid systems by changing the concentration. So it's another way of doing it. So liquid crystals are an intermediate state between the solid and the liquid phases, and they can be accessed by melting appropriate solids, and at a certain temperature they will turn into a liquid crystal and then a liquid. And you can see some of the types of liquid crystals that exist: soaps, biomembranes, electronic materials, and structural materials. And I'll be talking about some of those. Well, to start off with, I thought I would actually try and demonstrate this phase transition with a sample that I've got. And if all goes well, we can do this. I should introduce my assistant, if that's the right word, Luis Cortez, who is one of the Die-Struck Fellows working in Oxford, and he's been bullied into sitting behind the desk there and working all the technology. So, but anything that goes wrong is, of course, his responsibility, not mine. No, I don't mean that. Okay, so you want to switch to the next slide, which should be a blank, I think. No, go back. The next, okay, that's the next slide, is a blank. That's fine. Yeah, right. I think we may need. Is that on the camera now? Is that on the camera? No, it's not. We're on the blank slide. We need to.
Oh, sorry.
Yeah. No, that's the blank slide in the. Yeah. This is a small sample of a room temperature liquid crystal. Some of those at the front will be able to see that it's a turbid material, and it's rather an important material. This is about the amount of liquid crystal that is in your large screen TV, and in fact, it is the material that kick-started the liquid crystal display industry. It's a room temperature liquid crystal, which it was very important for that development, and I'll be saying a bit more about that later. Right, so let's see. I should say that at 20 degrees, this would be solid. It should be solid, but except it was solid, but it supercools fairly easily. So the melting transition from solid to liquid crystal, I'm not going to show because it's already melted, but it's a turbid liquid. And I'm going to heat it and we'll see what happens next. So if we put it in the right place there, right, there we go. And going. Yeah, I think it's going. Yeah. There we are. You can see it's beginning to clear. So that I won't take all the time. It's clearing slowly. So that liquid that we had before, or fluid, I should say, that was turbid, has had another melting transition, apparently, to another fluid phase, which is the ordinary liquid. And if we leave that in time, it'll come back to the liquid crystalline state. Right, so can you go back to the slides and then... Next slide then. Okay. The first experiment like that was actually done more than 120 years ago by a biochemist by the name of Friedrich Reinitzer, and it wasn't on that material. It was on a material that he was studying as an extract of carrots, and it was a cholesterol derivative, cholesterol benzoate, for those that understand these pictures. And he found that it did exactly what I've just demonstrated, that the crystal melted, in this case at 145, to a turbid fluid, and then on further heating up to 178, it went clear. So there are two melting points. And really that's as far as Reinitzer could go in his interpretation of the situation. He was a chemist by training, and he didn't have any other techniques at his disposal. But he had heard of, next slide please, he'd heard of a man by the name of Otto Lehmann, who was working in Dresden, but quite soon moved to Karlsruhe, who had invented a new type of microscope, a microscope that had a hot stage. You could heat it, and so you could see what happened to samples on heating, whereas previously microscopes, which again we've been introduced to, were only operated at room temperature. Now, and it was a particular special sort of microscope. It was a polarising microscope. Now, polarising microscopes in the 19th century were extremely important because they enabled the study of minerals. Geology and mineralogy in the 19th century was extremely vibrant topic because of mining considerations. And the polarising microscope, which is just an ordinary microscope, but with polars. Let's see if it works on here. Yes, I'm sure you can see, with two polarizers. And if you put them, if they're crossed, then it's black. And if they're parallel, you can see through it. And the remarkable property of the polarizing microscope was that it could, under the polarizing microscope, liquids and gases, if you wanted to look at them, appeared black, and the polarizers were crossed. But if you put minerals and crystals underneath, then you could actually see them. And if you changed the orientation of the crystal, then you got different images, and this became extremely valuable for identifying crystals and working out details of the crystal structure. So the polarizing microscope was very important. Now, Reinitzer sent his samples to Lehmann, and Lehmann then spent quite a long time, most of a year, studying these. And this is one of the images that he saw. He saw strange objects. You can see some of them look rod-like, that they hadn't seen in previous circumstances, but these could move. They were flowing, and they could flow into one another, they could coalesce, or they could separate sometimes. This was a thin film, but he also studied in detail droplets, and these are some of the images of the droplets that he studied. And there are pages and pages and pages of these pictures. They're, of course, not coloured photographs. These were hand-painted by either Lehmann or his technician, peering down the microscope. And he claimed to see all sorts of phenomena. And as I will explain later on, he was quite... He was so convinced about the remarkability of this new material that he thought he'd discovered the secret of life, because within the droplets you could get apparently cell division and then uncoupling as well, all sorts of phenomena, but more of that later. Next slide, please. Now, the news got out. They published a few papers on this, and others picked up the story. And two chemists in particular made lots of, or not a lot, but a number of other materials to study, so that there were materials around for people to look at. Let me mention, first of all, Ludwig Gattermann, working in Freiburg, and he actually made the liquid crystal material, which is called Pariazoxyanisole, or PAA, which became the standard material for about 30 years. Everybody made measurements on PAA. But Daniel Vorlander was actually much more committed to liquid crystals, and in the period of his work from the 1900 to 1940s, he produced over 1,000 liquid crystal materials, which he stored in his cigar boxes. As you can see, a lot of smoking went on in the chemistry labs at that time, so there were plenty of empty cigar boxes. I have to say that these cigar boxes have in fact survived in Halle, which is where Vorlander worked, and it's still possible to see them. Now, next slide, please. Which is a blank, I think. Oh, no, okay, before I go into I've got a demonstration of that. Let me anticipate the demonstration a bit, just to tell you what we know about the structure of liquid crystals now. And of course, as a result of the work that was done in the first decades of the 20th century, the chemists realized that certain shapes of molecules would form liquid crystals and other shapes wouldn't. And the characteristic feature of a molecular shape that caused it to form a liquid crystal was that it was elongated. Later on, they were able to make disc-like or star-shaped molecules that also form liquid crystals, but that came later. But initially, they were all, so the liquid crystals were formed by rod-shaped molecules, extended molecules. Now, to put you in the picture, as it were, we can now have a pretty good understanding of the basic structures of liquid crystals, and these are computer simulations of elongated particles, and the three states that I'm demonstrating here is the crystal state, where the particles, or molecules if you prefer, are all organized in terms of their orientations and positions. This is how they would be in a crystal lattice. And then if you heat that, then the crystal melts, and you have a complete disordered array of the elongated molecules or rods, which is the liquid state. But in between those two states, over here, is the liquid crystal state, in which the orientations of these elongated species are ordered. That is, they're all pointing roughly in the same direction, but the positions are completely randomized. so that this intermediate state, which characterizes the liquid crystalline structures, is where we have order of the orientations of molecules, but not the positions. So this is still fluid. The molecules can move around, but there's no translational order. In fact, in other liquid crystal phases, as we'll see later, there are phases which have a degree of translational ordering, but they're still fluid phases, and they still have orientational order and some translational disorder, and they're still liquid crystals. Right, I've got a movie, thanks to Louis, of the. Now these are rods. These are fluorescent rods, and this is what we can do today. And I said with colloidal systems, instead of changing the temperature, we change the concentration. And so this is a sample of fluorescent rods of about 3-4 microns length. They've been labeled with fluorescent dye, so you can actually see them. And on this picture, there's a density gradient. The concentration is increasing as we go down. And at lowish concentrations, we've got fairly random motion, which is the equivalent to the isotropic phase, or is the isotropic phase. Then there's a phase transition here going into the liquid crystal state, and this is the liquid crystal state that we call a pneumatic state. And then further down, we have something that is much more solid-like, and it may be a solid or a glass, or it may be one of these liquid crystal states, a smectic state, which has got some degree of translational order. And sometimes you can see layers forming, which is characteristic of that. Okay, thanks for that, Louis. This orientational organization and translational disorder occurs in lots of things. I rather like this picture. This is a liquid crystalline state of sheep, and you can see the positions are randomized, but the orientations are all organized. And for the experts in the audience who like to study defects, we've even got our own defect there. So. Next slide, which I think is a blank slide. Right, now to another demonstration. I said that the German chemists of old kept their liquid crystals in cigar boxes. Well, I've got a cigar box here, and it's got some liquid crystal particles in it. You can probably see them. They're all nicely aligned, and apparently in a layer, but actually that's because they're in a box. What is interesting, they're not. That is to say, they're organised in 2 dimensions, not 3 dimensions, and they're rather special particles as well. Let me take one out. Can you put that on the table? They're chiral particles, and that is. They are left-handed or right-handed, depending on how you want to define them. And you will all know about chirality or handedness. Most people are achiral. That is, they have a mirror plane of symmetry that goes down the centre of them, assuming hopefully that they've still got all their limbs. And it's rumoured that the perceived beauty of a person depends on the extent to which the left-hand side of the face matches the right-hand side of the face. So it occurred to me that when you're next posting an image on a dating site, I suggest that you take a picture, you Photoshop it, and flip one side, put it on, and see if your chances are better. I haven't tried it. Okay, so we've got these chiral particles, And what we really want to know is how they organize themselves in 3 dimensions. Well, this is a sort of a way of trying to demonstrate that. It's a bit artificial, but never mind. And I'm just stacking them up and in a fairly random fashion to see what happens. Whoops. Say random, it's almost random. I don't want to build any defects into it if I can avoid doing that. Okay, so there we are. They're sort of randomly arranged. The orientations are randomly arranged in 3 dimensions. But now if we want them to be liquid crystalline, now liquid crystalline order means that we want the directions to be as parallel as possible. So let's try and line them up, and hopefully it'll work. Let's see what happens. Yes, you can probably come and assist too. I can, yeah, okay. So we're making them as parallel as possible. We're not forcing them, we're just spinning them around to let them find their most comfortable position. I think that may be a defect, is it? Well, we're almost there. I think you can see what's happening. We're getting a helix formed. And I probably don't need to go right to the top, but I think that'll do. I think you see the idea. So these chiral rods have stacked up in a helical arrangement. And these helical arrangements, so can we go back to the slides, have a rather special property. There's the stack of twisted rods forming a 3-dimensional helix, and it's still a nematic liquid crystal, but it's a chiral nematic liquid crystal. And in fact, the first material that Reinitzer studied was cholesterol benzoate, which in fact is itself a chiral material. And this phase, this handed nematic liquid crystal, is actually called, or was called for a long time, a cholesteric liquid crystal, because it was shown by derivatives of cholesterol. Now, if you align these helices, which is quite easy to do, all you need to do is to make sure that the bottom molecules are aligned in a particular uniform direction. You make a thin film of this, and then you look at it under various optical conditions. You find that it reflects light in a particular way, and in fact the only light that is reflected back is actually polarized light, but it's not linearly polarized light, it's circularly polarized light. And I won't go into, if you don't not familiar with that, well, you'll have to take my word for the fact that light is a wave motion. It can go up and down or side to side, or it can also execute a sort of a circular motion going through space, and that's circular polarization. Now, this particular material of cholesteric liquid crystal in a film selectively reflects circularly polarized light at the same wavelength, the same color, corresponding to the pitch of the helix. Now, the interesting thing is that you can change the pitch of these films by changing their temperature, or you can apply fields, you can apply pressure, do all sorts of things. So you can change the apparent color of the film by changing these external variables. So this becomes a sensor. In fact, this was the first application of liquid crystals that was found, and the pitch varies with temperature, and hence the color changing the temperature. So have the next. And so this is the origin of the liquid crystal thermometers, which you may well have seen in different circumstances. This is a thermometer for parties. It's got a wine region and a lager region. This is a more serious application. And I'm going to pass this round. This is it's a rather nice, it's a very simple example, a nice example. It's a room temperature thermometer. You can play with it yourself. The only downside of these liquid crystal thermometers is that the blue is hot and red is cold. That is because usually the pitch of the helix gets shorter as you cool it down. And no, the other way around. Is that right? Yeah, the other way around. So it's that's. But you can get materials that work the other way. So I can pass that round, and you can. Now, the way it works, actually, there are stripes there, and each stripe corresponds to a different mixture of liquid crystal material, so that the range of temperatures over which it changes colour is different for each band. And so that's how it works as a thermometer. Okay, next. Right. I said that there are a variety of liquid crystal phases, and some of them, and the one I've been talking about has been the nematic phase, in which there's orientational order but no positional order in 3 dimensions. And the chiral version of that is the cholesteric phase. But there are many, many phases now of liquid crystal phases, more than 20. And the smectic phases are liquid crystal phases in which the molecules, or indeed the rods, are orientationally ordered. They may be ordered perpendicular layers or at an angle to the layers. But there are layers, so that is, there is some translational organization. That means that you can detect these in X-rays very easily, and you get proper Bragg reflections, but only from the scattering due to the layers. That is, they are liquid in the plane of the layers, but solid-like perpendicular to the layers. They are one-dimensional solids, if you like, two-dimensional liquids. And indeed, there are another class of liquid crystal known as columnar, in which you have solid-like, that is a lattice organization of positions in 2 dimensions, but along the columns they're liquid-like. So you have a one-dimensional fluid, liquid along the column, and a two-dimensional solid perpendicular to the columns. So there's and lots and lots of variants of those. And I should say that the pictures I put up there are just obviously models, and these models could apply equally to molecules or to rods. So it's relevant for the work of this network in terms of colloidal systems. So, next. Right. Now, how can we identify these different phases? And we use the polarising microscope. And the wonderful thing about the liquid crystals under the polarising microscope is that they are solid-like. You get coloured images resulting from the fact that the molecules have some orientational organisation, and this orientational organisation means that the optical properties vary in different directions, and the fact that the optical properties or refractive indices are different in different directions means that you get interference effects, and this shows up as colours, and the arrangement of the colours with experience, you begin to be able to detect different phases on the basis of what they look like under the polarising microscope. So it's a very valuable tool for liquid crystal scientists. Right, so here's just some examples, and they're very pretty. That's why I like looking at them. This one I'm very fond of. This is of the nematic phase. You can see it's pretty, it looks sort of fluid, but the interesting thing for me is that these lines are rather special lines. They're actually fluid defects, and you can see these very clearly in the microscope. So the liquid crystal phase has something in common with crystalline states in that it forms defects, whereas a pure liquid, there are no defects in it. This is a smectic phase, a layered phase. You can see it looks a bit more rigid. It still flows, but it's more solid-like. This, again, is a picture I'm particularly fond of. This actually shows a range of textures of a chiral liquid crystal, a chiral nematic phase, and it's actually, there's a concentration gradient across this as it happens, and you get these wonderful images. This picture here was provided by Dirk for me, and it shows a columnar phase, this is characteristic of columnar phase. It doesn't have quite the aesthetic beauty, I don't think, of these phases, but it has some qualities, and the suggestion was that maybe Vincent van Gogh was drawing his inspiration from what he might have imagined columnar phases to look like. Who knows? Okay, thanks. In the late 1970s, actually it was about 1980, I was hired by a large American corporation to look into the prior art, so-called, of liquid crystal displays. And the reason for that was that, as I'll explain later, that they were going to challenge patents that had been filed for the new generation of liquid crystal displays. It was as a result of that particular task that I came across this gentleman, Vesvolod Fredericks, a Russian, and his papers, and he had got interested in liquid crystals in the 1920s and was working away to find out a little bit more about the physics and optics of liquid crystals. And the important thing that he discovered was that you could change the orientation of a liquid crystal by applying either an electric field or a magnetic field, and as a consequence of changing the orientation, then the optical properties of the film of liquid crystal changed. In fact, what you could do if you have polarizers top and bottom, you can create an optical switch which switches from being black to white or white to black. Now, an optical switch is the fundamental aspect of any electronic system of display or communication, and so this potentially, had a lot of potential, as we'll see later. This is a threshold effect. That is, you apply a voltage and nothing happens until it reaches a certain value, and then the change occurs. And in fact, the switch back is driven as well, not by a field, but there are elastic torques on the molecules, or rods, as I've represented them here, from the treatment on the surfaces. So this is the Fredericks effect, and he actually initially discovered the effect using magnetic fields, and the next slide, I think, is the demonstration that we're going to try and show you. And this is, we take a film of liquid crystal, and it's going to be between polarizers, and the crystal is aligned so that it's perpendicular to the film surfaces, and we're going to apply a magnetic field to this film, and what it's going to do is to change the orientation of the molecules in this film, and as a result, it'll change the refractive indices in particular directions, and you'll get interference patterns that might not look as pretty as that, but what these interference patterns are mapping out is the orientation of the liquid crystal within the film. Now, the demonstration that I've set up here is actually going to be a rather slow in time scale, but in fact, if you do things right and you have thin films, you can switch on the millisecond time scale. So these are fast optical switches. And so let's do that now. So we've got two polarizers. Put the sample on. Oh, we haven't got the camera there. Okay, you want to put the camera on? Right, okay, there we are, that's not bad. Right, so that is the sample, and in fact, it should be perfectly black, but it's not quite. Probably there's a slight variation in thickness, and maybe the light is not totally collimated. Now, we're going to see what happens applying magnetic field. You need rather strong magnetic fields, so I've got some of these rare earth magnets, and let's see if I can demonstrate the switching effect with a magnetic field. There we are. So the rings that you see are a direct consequence of the alignment of the liquid crystal molecules in the thin film switching in the magnetic field, and the more rings you see, the greater the deformation. And so this is the basis of switching in liquid crystal TVs. You're doing it with electric fields, not magnetic fields, but the principle is the same. So that's, I've turned the magnet around. It's a transverse field now, but you see beautiful pictures. Okay, that's good. Let's go back to the slides. Okay, next slide. No, okay, it's a bit slow. Right, and I want to tell you a little bit about Fredericks, because he's a great character. He came from a noble family in Russia. His father and grandfather were governors of eastern provinces in Russia, working for the Tsar. He didn't follow the career path of his father or grandfather. Westerhof wanted to be a scientist, and he studied in Switzerland and in Germany. But and he escaped the troubles of the Russian Revolution in 1917, which killed his father. But he went back to Petrograd or Leningrad and studied there and was doing research in the State Optical Institute until around about 1934, when you will know the story of Stalin's paranoia and the battles that were going on within the hierarchy in the administration. And there was a coup against Stalin in Leningrad. And as a result of that, the local Communist Party secretary was killed, and this was an excuse to round up all of the intellectuals in Leningrad. 100,000 were rounded up and disposed of one way or another. Sadly, Fredericks was amongst these, and he was eventually put on trial. These were this is a transcript of his trial, and well, you can read it as well as I can. Were you going to commit any acts? Well, what specific actions did your organisation carry out? And I personally don't know any. Well, the transcript of the trial was not really relevant. He was guilty as he walked into the room, and he was sentenced to 10 years in a labour camp. He was already 50 when this happened, and sadly he didn't last. He died in the Gulag. But He was no ordinary prisoner. He was an academic. He was well connected with many in the Russian establishment, and in particular, he was a brother-in-law of the composer Shostakovich. And Shostakovich was thought to be close to Stalin by some. I think that our view of that is changing, but even the intervention of Shostakovich and other senior academicians in the Russian Academy of Science couldn't save him, and so he perished in the Gulag. However, a physicist that was imprisoned with him said that Frederick still went on working, and in fact he worked out the elastic theory of liquid crystals to explain his effect, the switching that I've just shown you. So the story is, it's a very sad story, because although we've got letters exchanged between Frederick's and his family, his wife was also sent off to exile somewhere else. His son was looked after by his grandparents in Moscow, and as far as we can tell, he never saw, after being sent off to the Gulag, he never saw his family again. A sad story. Of course, when the regime changed under Khrushchev in the 56, Fredericks was rehabilitated a bit late, sadly, but he's remembered through the Fredericks Medal, which was introduced by the Russian Liquid Crystals Society in 1997, but also he's remembered through every electronic device that we use today using liquid crystals, which use the Fredericks effect. Next slide, please. But the first liquid crystal display didn't use the Fredericks effect. Actually, the RCA was big industry making displays, conventional displays, cathode ray tubes, and but they were investigating other possible display technologies. In the period after the Second World War, the physicists turned their attention from war-like matters to applying them for peaceful purposes, and there was a huge development in all sorts of technologies. The microwave oven was invented, and lasers were discovered, and all sorts of other things. And it was decided that we should look at other possible ways of displaying information, that is the man-machine interface, which didn't require large vacuum tubes, as in cathode ray tubes. Well, to cut a long story short, RCA came up with an invention. It depends on a phenomenon known as dynamic scattering. It uses rather unstable materials, and in fact for it to work they actually have to be impure, because it relies on ionic circulation in the films, and eventually the displays die. It was announced with great acclaim, this will have a major effect on the electronics industry. In fact, it didn't. And in 1972, RCA stopped all of their liquid crystal activity. Next slide, please. One of the people working in RCA was Wolfgang Helfrich, which might be known to some of you in the audience. And he, while working in the liquid crystal group in RCA, had come up with an alternative idea about a display that might work, based on Fredericks actually, but not of Fredericks' original configuration, which, if you remember, had these two surfaces parallel to one another, but a configuration in which one surface was twisted through 90 degrees with respect to the other. The switching effect was essentially the same, from a transverse alignment to a perpendicular alignment, and it worked in exactly the same way. It provided an optical switch between polarizers. Well, because the liquid crystal group was going to close down, Wolfgang Helfrich had to find another job, and he did find another job with the Swiss company Hoffmann La Roche. I should say that he'd presented his idea to the guy on the previous slide, Hallmeyer, who said, no, that'll never work. My display is much better. My display is going to make billions for RCA, but as I say, it didn't happen. So Helfrich went away, left the company with this idea in his head, and he met up with Martin Schatt, who was another physicist at the time, had been working in Ottawa in Canada, and they both joined this Swiss company, Hoffmann La Roche, which had been previously largely pharmaceutical and cosmetic company. Within a matter of months between them, they had made the first twisted pneumatic display, which you see there, and and it was patented, and then a huge, well, as I say, the patent battles began, of which I was involved, whether this was new or not. Eventually decided that it was new enough, so lots of people made lots of money, or rather lots of companies made lots of money. The lawyers, I suspect, made most of the money, and this was marked the beginning of the display industry. Next slide, please. Right, there were still problems, which was that the materials that were being used in the first display of Schatt and Helfrich were not that good. In fact, initially, they weren't even liquid crystalline at room temperature, so the whole display had to be heated up in order for it to work. But a breakthrough came with the United Kingdom chemist George Gray working at Hull, but he was actually working under contract with the Ministry of Defence, and he discovered this material, pentyl cyanobiphenols, and this is actually what I showed you the demonstration with. This is a sample of this material, which was liquid crystalline at room temperature, very stable, didn't deteriorate under conditions of electric fields or light or anything. I picked up this was quite a nice cartoon. This was published in the Swiss Watch Journal. They weren't terribly keen on the idea of liquid crystal technology, and so this is a cartoon indicating their lack of enthusiasm about the new invention. However, I should say, I do think the last laugh is with them, because they can charge $50,000 for a watch, and we can only get a few euros for a watch display. So it didn't actually change much. Right, next slide, please. Okay, so the rest, as I say, is history, at least in the display business. The first liquid crystal TV was produced in 1983 by Seiko. That's 5 centimetre diameter there, and then it went on to produce these very big, fancy, high-definition screens. And here's a mock-up of a 3D glasses-free laptop, which I've actually seen and had to available to demonstrate. It doesn't look quite as dramatic as that, but the liquid crystal technology will go on. And I should say that the modern displays use the effect that I showed you initially of the Frederick's effect. They no longer use twisted pneumatic configuration. They use something called vertical alignment, where the liquid crystal film is, as I showed you, initially vertical, and then it switches to horizontal and then switches back. And that is the Frederick's effect, and that's what is in all of the displays that you see today. Right, next slide, please. Now, this is going to have to be quick because I've only got 4 minutes. Going back to Lehmann, liquid crystals and life. Lehmann became obsessed by the idea that liquid crystals were the answer to the secret of life. And this was partly inspired by this observation that in the mid-19th century, Rudolf Virchow had been studying, using conventional microscope, various biological samples. And here is an image that he drew, or his technician drew, of human nerve fibers underwater. And so this was available in the literature. Lehmann was studying various mixtures of things in the context of liquid crystals to see what he could do. And by mixing a soap, which would be a salt of oleic acid and water, or rather looking at the contact region between water and oleic acid and soap, he found these fibers growing, and he made this connection. And what's more, he had determined that both these fibers were liquid crystalline because they had fluid-like characteristics, but he could see them in the polarising microscope. They had all the optical properties of the liquid crystal, exactly as did the fibers that he'd grown in this water soap system. And so he was quite, I won't say convinced, but he was very enthusiastic that he had discovered the secret of light. And this is Ernst Haeckel, who made this remark that the discovery of Lehmann was the ultimate on the understanding living systems. Okay, can I, next slide. Right. The importance of liquid crystals in living systems, and this is going to be very brief. I should go very quick, but hopefully I can show you this. This is a particular sort of beetle, and I mentioned the reflection properties of cholesteric liquid crystals. Now these beetles, scarab beetles, reflect light, circularly polarized light, just like cholesteric liquid crystals. And in fact, if you analyze the properties of the reflected light, they look exactly as the models have been calculated for reflection of light from cholesteric liquid crystal phases. The shell of the beetle, the carapace, is not liquid crystalline, but the suggestion is that at some stage in its development, it went through a liquid crystalline state. The other point that I want to make, which connects with what has been said by Dirk and Roel, is the scale of the structures. The scale of the structures in biosystems are in the sort of 10 micron, in the micron, in the tens of nanometers to micron scale. So it's not unreasonable that liquid crystal structures should be important in biosystems. So let's see if we can do this demonstration. Here are the beetles, which we're going to put on the camera, hopefully. This won't take a minute. Can I have 5 minutes more, Dirk? No. Right. Can you? Yeah, I think you can see the beetles there. They're greenish. Right. Now, here's a pair of viewing glasses for a 3D TV. One of them is a polarizer for left circularly polarized light. The other one is a polarizer for right circularly polarized light. So we're going to put this. I'll put it in front of there, okay? And
maybe on the camera.
On the camera, okay, let's do it on the camera. Oh, can we see? No. Do it again. Quite. Yeah, you can. I think you can see that it's still showing on this one. Oh, what's happened? Perhaps I'm not in front of it. Yeah? It doesn't seem to be working very well. Let me try on this one. it may be that they're being illuminated by unpolarized light from... No, well, I think you may have to come down and see for yourself. Hmm? Yeah, try it afterwards. But one of them cuts out the light totally and the other one doesn't. So just in 2 minutes more, is that okay? Okay? Wrong way. Right. Biomolecules such as proteins, nucleic acids, lipids, and so on all form liquid crystalline phases in water. And the first observation of this was by J.D. Bernal. Here he is with his research student Dorothy Hodgkin, and they were investigating tobacco mosaic virus, which are rod-like particles. And rumour has it that they've put a solution of this in their goldfish bowl, and they looked at the goldfish bowl between cross polars, and they saw images that were characteristic of a liquid crystal phase. They interpreted this and did X-ray measurements, and they indeed found that there was orientational organisation of TMV particles as in a liquid crystalline state. Now, I don't think Pavlik is in the audience this morning, but he reproduced this experiment, and here it is. It's not actually TMV, this is FT virus solution between cross polars, and he's about to put a goldfish in. Now you see the optical pattern there, these interference images, which is characteristic of a pneumatic liquid crystal phase. And so there we are. The poor goldfish was exposed to liquid crystal. No goldfish were harmed in the production of this movie, I'm told. So, okay. And so the liquid crystal particles are important in lots of different aspects of living systems. In particular, they form the membranes of cells and, whoops, can you go back? This quote I put up there from a philosopher, not a philosopher, a biochemist from the 19th century, that all of life originates from cells and vesicles. This is a part of the cell wall containing lots of proteins, and vesicles are basically cells but without the proteins. They're sort of empty cases. But the important thing is that it's the lipids which are forming a smectic-like bilayer in the walls, and so the liquid crystals are important in life. So well, I'm running out of time. Let's just quickly go through. Liquid crystals are also formed by things such as spiders or silkworms, and they are producing main chain polymers that are aligned in a liquid crystal state, and they're extremely strong. The first example of this was Kevlar. It's an Aramid fibre discovered by Stephanie Kolek in DuPont, and this produces extremely tough materials, which you're going to see in a moment. Okay. Bridges, bulletproof vests. Here's a bullet being stopped, and I think, can you go to the end now? Okay, skip that. Yeah, just go back one slide. I should say this, that theory is always neglected or is often neglected in some of these scientific developments, because the public appreciation of a TV screen or a new drug or something is vastly outweighs all of the hard theoretical work that has driven this discovery. So it was quite good to know that, or to see that Tejin was actually given the Nobel Prize in 1991 for his work on developing theories of soft matter, in particular liquid crystals. Lehmann had been proposed for the Nobel Prize on a number of occasions and failed to get it. Of course, there are lots of contributions to liquid crystal science from Dutch people, and I mentioned Ornstein, who worked up the road in Utrecht, who was sadly, like Fredericks, was another victim of the trauma of the Second World War. He was displaced from his position in the university and he died shortly afterwards. But he made very, very valuable contributions to the theory of liquid crystals. And then finally, coming back to Eindhoven and Philips. Philips was a big company in the business of liquid crystal displays, but sadly in 1999 I think they sold they merged with a Korean company and was finally sold off in 2003. So, but I'm very pleased to be staying in the hotel that is inside the old Philips building, and so there we are. We have to. Sorry to have gone on longer than I should, but and here's some thanks to the die-struck people, Merck, who provided some of the materials, Sharp in Oxford, and Manchester. So, and thank you very much.
Thank you very much, David. I should also point out that David wrote a very successful popular scientific book about the history of liquid crystals, and it's available in English or Japanese. Not Dutch. There's a little time for questions, if there are any burning questions.
Well, I'm
not at the moment.
I'm around. Yeah.
David's around. We can have a look at the Beatles later.
Yes.
Now also,
sorry about
that. Time to thank our two speakers again. Move on to the next phase of this public lecture. Yes. We do it here? No. Yeah. Okay. Come in. Okay. Can I just introduce the last part of our outreach event? These are colleagues from Tejin Aramid, the fibre company, the successful fibre company. Erik is in the network and he brought some of his colleagues to demonstrate. Well, they'll show it once how to make fibers, and then you should all come down and do it yourself. Try to make the longest. There's a challenge there. Here's a colleague of mine, he's a real expert in
Hello, good afternoon. In Tejin, he will help you and assist you as well. Ines, he's part of the expert as well.
Yeah.
And then you can have a go for yourselves.
Yeah.
So, please.
Okay. Okay. Like was mentioned, this is a small, funny experiment to show you how the spinning process of Aramid yarn is done. I have two different liquids here, just water with some salt and an alginate with some carbon black to make it, of course, black, otherwise you cannot see it. The goal is to make, as Erik mentioned, a long yarn. I will help, and Erik and Ina will help you with filling this needle. We'll do 1 milliliter of spinning dough, as we call it, in the syringe. I will put a needle on it, and then you can spin the liquid out in the coagulation liquid. So we make from a liquid a solid yarn. It's done like this. I will try to make it air-free and just put in 1 milliliter or something like that. We will clean it for you. We will put a needle on it. And if everything goes well, a very important thing is that you have to put the needle under the coagulation liquid. Not above, just under the water. And then smoothly press and turn around in the water. And
That
you
looks
see,
simple, but
What's your world record?
no, there is no world record, but we also do this experiment on for children. And the longest yarn I can remember is about 4 meters. Just a 1 millimeter fluid.
so keep that.
So, and now it's a little bit solidified.
The game is on. No.
Hey, and there is your yarn.
In one piece.
In one piece. So this is the reference. So I would like to invite you all to have a try. Yeah,